16 Apollo astronauts. Okay.
Okay, and I'm going to let there won't be too many people on Zoom because we wanted to keep it kind of just, but Jay doesn't do Facebook.
Sure.
And
Mhm.
there's people here that don't do Facebook, so we'll be on here. So
And
let me
I'll be
just
looking
start
at my
that.
Facebook screen to see if the local school's asking questions here.
Okay, yeah, I've got some questions also from students too.
Students, yeah.
Let me admit everybody. And hopefully the speaker, in other words, when you're speaking, you should be the main person on. So if that's not the case, let me know, and I'll hopefully, in fact, can you test right
Yeah.
now, Laura?
If I'm, yeah,
There you
I'm
go. Okay,
speaking. I don't
okay,
hear anyone else, I think.
good. Okay, good. Okay, I'm gonna let my other people in here. Here we go.
Yeah, and if you don't hear me or anything, let me know, obviously,
Okay,
if something
okay,
drops out or you don't see anything.
okay. Good morning, Mark, and good morning, Bet. And Jay should be connected to his audio right now. Still connecting. Okay, it's 9:31, so I'll get started. Good morning, everybody. Welcome to a long-awaited edition of Science at Home interview with me, your host, Charles Fulco, with co-host Andy Poniros from Cosmic Perspective, WPKN Radio out of Bridgeport. And I love being on with Andy because we just have a great time and we always have fun talking about timely topics. And this one is about as timely as it gets. Andy, we're going to be talking with our special guest, Nora Leutzgendorf, today about the James Webb Space Telescope. And thanks for coming on with me, Andy. This is always fun when you're a co-host.
It's always a pleasure. Thanks for inviting me, and this is exciting. It's been a long time, and we have this opportunity to talk to Nora. It's wonderful, and looking forward to it.
Yeah, and a nice hello to everybody on Facebook Live this morning. And I know I'm off school today. Luckily, we had so many teachers that decided they didn't want to teach today in my school. They decided to give the entire district a day off. So to those of you who have to teach, all is not lost because I know some of you are already watching this with your students and sending in questions. So don't worry, it's Friday, and this is hopefully the best part of your day. And also, thank you, Nora, for coming on. It's a pleasure to have you. And T minus 1 month and a week, pretty much until the launch of the James Webb. And tell us a little bit about yourself. I've been reading up on you, and it's fast. You have a fascinating career and background. And tell us a little bit about yourself and how you got involved with the James Webb project.
Okay. Yeah. Thanks for having me. So yeah, I'm Nora. I'm German. So yeah, I did all my
I
education
thought
in
that was a
Germany. I did
Brooklyn
my
accent.
no. Thank you very much. No, no, I know you made a joke. So I did my PhD in Germany. Actually, I did it at the European Southern Observatory, which is the place who runs all the big telescopes in Chile. So I was always drawn to really big telescopes. And when I was studying, I was going to those telescopes and observing. And then I became a postdoc, a research fellow at ESA, the European Space Agency, and I went to the Netherlands. And from there, I got this really great opportunity to basically drop everything there and come here over to the US and work on James Webb. And that's what I've been doing since 2015 now.
Nice. And kids, in fact, one of my first questions, for some reason, this must be one of my, I should just say it every time. I always get students that want to know, how did you come to be what you do? Like, what did you do in school? Anything special? What courses did you take? Because we have a lot of kids who are very space, knowledgeable, and they want to become future scientists and future astronomers, and they always want to know what should they be doing, what should they be taking in high school and university.
That's a great question. I mean, I come from a different school system than the US, but in my case, I was able to specialize in math and physics in like my last 2 years of high school, and that's what I did. I mostly did it because I was good at it, but I also realized I wanted to do astronomy, and that I had to do physics in order to do this. So it's mostly my study was mostly physics, and then I could specialize in astronomy later. But I always loved astronomy. My grandfather, who passed away in 2013, he was the person who kind of got me into astronomy. He talked about black holes at breakfast, and he had a little telescope. And then I got my own telescope. And this is how I was, from the moment on, I knew I wanted to do astronomy.
Did you So how old were you again when you got your first telescope?
I think that's a good question. Probably around maybe 14,
You
15.
registered for a talk by Carol Strauss a year ago. Look in your email.
Oops, sorry. We had
I hear somebody else.
yeah, hold on, Jay.
No,
Okay, let me, Jay. Okay. Okay, sorry about that. Okay. So tell us again about you were about 14.
Yeah, 14, 15 was when I got my first telescope. It was a little refractor, so a lens telescope, and I looked at Saturn and Jupiter and its moons, and I loved it. It was in the middle of the city. I lived in Leipzig at this point. This is a city in East Germany, former East Germany. It was still pretty light polluted, but I could see most of the main astronomy like bodies in the sky.
Yeah, and we've had talks about light pollution on this show, and I'm active. I know Andy's active in this also with the International Dark Sky Association, and it's so important. This is a whole other topic, but so important for us to preserve the night sky, because had you not seen the night sky the way you did, you may not have gotten interested in pursuing this. So don't worry, we're on this, and we're going to keep going to preserve the night sky. So I'm glad you mentioned that. Now, when you were younger, did you follow the U.S. space missions at all? The space shuttle missions?
A little bit, yes. It wasn't as prominent as it is now that everybody would watch it, but I definitely saw like the replays in the TV, and yeah.
Wow. And then I'll give the floor to Andy in a second, but I have another question here from a student. Did you ever want to become an astronaut?
So this is a question I get often actually as an astronomer, and my answer is usually no. I'm afraid of flying. I'm a nervous flyer when I'm in the plane. I cannot imagine how I would feel when I go into a tiny little capsule to space. However, if I would ever get the chance by somebody to go into space, I would probably just do it and just overcome this fear, because it's something once in a lifetime, right? But I haven't had the desire to really pursue this kind of career.
Yeah, I'm with you. I would love to go, but I don't know how I would feel sitting on the launch pad. T-minus 1 minute to go. I don't know what I would do. But anyway, thanks for your honesty. Andy, you had some questions about the project itself. I know you had sent me some nice questions. Did you want to address a few of those?
Yeah, well, just one more question I also wanted to ask Nora is that how did she get involved with ESA? Was that through a program through the university you're studying, or was it just kind of you apply for a job kind of thing?
I did apply for that job. So ESA has this fellowship programs, which are postdoctoral positions where you can do your own research. It doesn't necessarily have to be connected to a mission, but it would be nice so that you have the expert in-house. And I thought that was a very attractive position because you had nobody to tell you what to do and how to do your research. You could completely independently do your research, and you would be in this great place where all these other things are happening. Since I was always drawn to like bigger telescopes and exploration and not just academic research, I thought that was like the perfect place for me. Yeah.
And how did that eventually bring you to the U.S.?
Yeah, it was this project. It was the position that I applied to become at this point then a permanent staff of ESA and to work on JWST as an instrument scientist. And this position came with going to the US and working here. And that was fine with me.
Great. I guess I'd like to also talk about the telescope a little bit. But what I think is amazing is that it's such a technological marvel, and I think a lot of people don't understand how much effort and time went into this. And I understand there were thousands of engineers and hundreds of scientists. We have NASA, ESA, Canadian Space Agency, 29 U.S. states, 14 countries, and more than 300 universities that worked on the project. Can you tell me a little bit about how long it's been since the project was an idea and how it came to be today?
Yeah, so the project's been going on since even when I was still in high school, right? Like one of the first ideas of this project I have is from 1996. That's when people, and it's maybe even earlier, but that's when people had this idea, hey, we're gonna put this really, really big telescope in space. It's gonna be in the infrared and we need a sun shield. So those really early ideas and I can show this a little slide about this later, is like it already looks a little bit like Webb today. So people had the main components in there. It looks very different because it was just a scribble, but yeah, this idea has been around forever.
Yeah, but I said, Bargin, for a second, we just had a question about infrared. Why did you choose to observe in infrared? And I think I know the answer, but I'll let you say it because you're the scientist.
So there's so many different reasons why we would want to observe in the infrared. The infrared, which is basically what you can call here heat radiation. It's like if you look at those cameras where you can see your own heat on your body, this is basically infrared. So this is a very long wavelength radiation. And it has this specific ability to peek through gas and dust clouds in the universe. So while Hubble observed all those beautiful pictures, we always sometimes see those dust and glass. I hear some music in the background. Is that normal?
Yes,
just saying that there might be some more disturbance,
yeah,
but I'm not sure.
Who's not here. Hold on. Yes, we have a non-muted person here. Thank you. Okay.
It's okay. It was nice music. It was like a classical music. Where was I? So infrared can look through gas and dust. We can go deeper into, for example, birthplaces of stars and planets or the very centers of galaxies. It can look at very cold places as well, better than Hubble could do. So we could really look at the cold disk where planets are forming. And we can look further back in the universe. As you know, things that are further back in the universe are also like further in the past, and they are redshifted because of the expansion of the universe. So if you have a telescope that is very sensitive in the infrared in this redshifted regime, you can look further back. And that's one of the things we're going to do with Webb. We're going to look at the very first galaxies and stars that were formed right after the Big Bang.
Now, one of our listeners in this morning, Dr. Jay Pasakoff from Williams College, he has much experience in that. So Jay, if there's anything you wanted to add to that during the interview, you are quite the expert, so feel free.
Okay, well, I'm looking forward to the talk, so we can talk.
Okay, thanks. Nora, I got another quick question here for you. This is a good question. This is from a student who must be up early. They're in Colorado. They're probably not at school yet.
Wow.
Yeah, wanting to know why. Let me just mix it. Okay, why? Okay, why is it important for the James Webb to replace the Hubble telescope? I guess meaning, has the Hubble served its purpose, and what's special about the Webb compared to the Hubble?
Actually, I'm going to talk about this in a second on my slide,
Okay.
so I'm not going to answer his question precisely because I have a slide comparing Hubble and Webb. So if he has still a question about it afterwards, I'm happy to clarify further.
Okay. Okay, excellent. Okay, and Andy, did you want to get back to the questions we had written out already?
Well, I don't know. I think, is it, Nora, would you prefer to go through the slideshow?
The slides, yeah, let's do the
Because
slides.
Yeah, let me
there's
just go
questions
through
I
the
have are about the
slides.
telescope. Yeah, let's go
Yeah.
through the slides. Sounds good.
Yeah.
Okay. Let me share this real quick. Are you ready for me to talk about this real quick?
Yes, please.
Okay. So yeah, I have only like 8 slides or so prepared just to show you like the overview of the telescope and what we're going to do and what's so special about this telescope and how this all came along. So first of all, the name. Some people might have wondered why it's called James Webb. Who was James Webb? James Webb was the second NASA administrator between 1961 and 68. So in those times when all the Apollo moon missions were happening. And administrator means he was basically the head of NASA. And he was a very major driving force for those Apollo missions and also in general science missions at NASA. So NASA decided to honor him and name the next big space telescope after him. So that's why it's called James Webb. Sometimes we just call it Webb. Sometimes we call it JWST, but that's where the name comes from. And here's the slide I was saying I'm going to talk about real quick. This is like comparing Hubble and Webb in one big slide and what is different between the two of them. The first big difference that we see immediately is the size, right? We have Hubble with a 2.4 meter mirror, which is a little bit bigger than a person, as you can see it in the comparison. And that was already very revolutionary to have such a big mirror in space back then when Hubble was launched. But now we have Webb, which is 6.5 meters high. This is like 3 storages of a building high. You see the little person as a comparison there, right? So it's a whole different dimension. And because it is so big, we cannot make this in one piece because this is very difficult. Even with telescopes here on the ground, with those mirrors that big, we don't make them in one piece. So we make it in segments. So Webb has 18 mirror segments that we can all move individually to make it a really nice, smooth, curved mirror in space. So this is the big difference. The next big difference is where they're going to be. So Hubble, as we know, is in an orbit around the Earth, 570 kilometers away from us. And I'm sorry, I'm European, I'm using metric systems here.
Oh, that's
you
good.
can calculate it in miles. Yes. So it's on an orbit. Now Webb, as we discussed before, is an infrared telescope. And the Earth, with all its like factories and humans on it, is really, really bright in infrared. So if we would put Webb around the Earth, it would be too bright for us. We couldn't observe the night sky because it would just be disturbed by the Earth all the time, and by the sun because we're going around the Earth. So definitely don't want anything of this. So that's why Webb will go 1.5 million kilometers away from us to the so-called Lagrange point 2, which is a semi-stable point in space. And it's basically past the moon, far away from us, so that it forms a line between like Sun, Earth, and Webb. And then we will all go around the sun in this kind of constellation. That sounds very crazy, but it has been done before. There's telescopes in Lagrange point 2 already. We know it works. And that's where we're going to put it, so that it's away from us, away from the sun, and can observe the sky undisturbed. And then we already talked about this, that it is in the infrared, why Hubble is in the visible, and Hubble gave us amazing science in the visible, but we have explored this, and Hubble is at the end of its life, but it has done everything you could imagine in the visible. So now we go in the infrared for those reasons, to look further back in space, to look now 13.5 billion years back into our universe. Yeah, this is right when the universe was born. And look at the first stars and galaxies. Hubble could already look far back, even without the infrared. We could go 12.5 billion years back, but we will go even further back with Webb. So this is going to be great. The last big difference that you have to keep in mind with Hubble and Webb is Hubble was serviceable. That means we could send astronauts up to Hubble and fix it. And we did, right? If you remember or read in history, when Hubble was first up there, it was basically blind. The mirror wasn't done well, so they had to go up and fix it. Something we cannot do with Webb, and that's also one of the reasons why we sometimes delayed during its time now here on Earth, because we needed to make really sure that everything is working properly, because we cannot go up there and fix it once it's up there. It's too far away. So these are the main differences to keep in mind, and I hope I answered the question that we had about this. So let's see, next slide. Yeah, here we go. So this is our timeline that we have, what's happening next. So we already shipped, and you might have seen the news on this, we already shipped the telescope from California at Redondo Beach, where it was assembled, to French Guiana. Why are we launching from French Guiana? That is the European Spaceport, and the European Space Agency, the place I work for, they have agreed to do the whole launch of Webb. Yeah, since we have a partnership between ESA, CSA, and NASA. When NASA does the full project, we had like different parts for these space agencies to be done. And one of our part is we do the launch. So that's why we launch from French Guiana. This is our spaceport. It's close to the equator, which is great for us to launch anything. And so now we are basically almost at the minus 29 days when we start building up these different stages of the rocket. And then very close to launch, so one day before, we have the full rocket and the telescope in the rocket. And we have launch 18th of December, very early in the morning for us here. It's at 7:20 in the morning for the Eastern Coast time. And then there come these different stages that you might have seen when you looked at other launches, when they start separating the boosters and the upper stage, and until the telescope is all by itself. And then 30 minutes after the launch, we will have our first contact to the telescope. And then we will take over, basically, NASA will take over. All this before was ESA's part, and then NASA will take over. Okay. So where are we going and why are we going to L2? I mean, I already told you why we're going to L2. We want to be undisturbed from the Earth, the Moon, the Sun. And so L2, 1.5 million kilometers away, takes about a month for us to travel there. And while we're traveling there, we will unfold the telescope. And I will show you this in a second, how this works. But yeah, so we will, the first 30 days, we will travel to L2. And then we have this like big loop orbit around L2. You cannot see L2. I on purpose did not put like a dot of there at L2 because it's not really a spot in space. It's a mathematical thing that we like orbit around. But you can see the telescope will then always be in this orientation. It has the sun shield. So the sun is like on the left. Oh, I'm not sure if this is left or right for you guys, but on the other side of the Earth. And the telescope will always point with the sun shield towards the sun. That means we have a very hot side of 85 degrees Celsius and a very cold side of minus 233 degrees Celsius. I think this is minus 300 Fahrenheit. So it has this really different sides, this telescope, because on the hot side, we have all our electronics, they can deal with the heat, and we have our solar panel. And on the cold side, we have our instruments, the instruments that detect the infrared light, and they need to be cold. And that's why we will always have this kind of orientation. And then you can see what are the next milestones. We have then in like 2 to 3 months after launch, we have our instruments turned on, and then we begin with this so-called commissioning phase where we start calibrating our instruments. That's going to be about 6 months. So I will have to be working for 6 months, and we will work in shift work because we have to have contact to the telescope 24/7. So we will have 3 shifts a day, 8 hours. And then depending on how you got, it's basically like working at the hospital, right? You will have different shifts where you work and make sure that everything goes right with the calibration. And then 6 months after launch, we will see our first images. We will have the early release observation images that will be shown to the public. There's pictures that are like objects that were chosen. They're still secret. We don't know what they're going to be, but they will be chosen, and they were chosen to show the public how great James Webb is. So 6 months after launch, you can think of when the first, you will see the first images. Okay, and then the question is always, how do you get such a big telescope into a rocket like this? Yeah, there's no rocket that would be able to ferry a telescope like this in this stage into space. And this problem had to be solved for Webb, and they decided we're just gonna fold it. So Webb is folded before we launch to fit exactly into Ariane 5. And you can see that here. If Webb is unfolded, it is as big as a tennis court. Yeah, nothing like this can be put into space, just out of like energy reason and everything. So we fold it and put it into our rocket. And then when we're in space and we travel to L2, we will unfold it again. And you can see this a little bit here. This is the unfolding sequence. We start flapping out the sun shield, and then we do the lateral unfolding of the sun shield. Then we separate our layers. We have 5 layers of sun shield. And then we clap out this little secondary mirror and the flaps of the primary mirror. And then we suddenly have a really big telescope again. And that will take 29 days. So for 29 days, we have to just watch and see that everything works out as we planned. And I think this is like what I wanted to say about like the overview of Webb. I want to finish with this little unfolding video because it's showing you the whole thing in real time, not in real time, and sped up time, how it will unfold. So all this, you see a little antenna unfolding there. You see now the sun shield rolling up, and then we start unfolding the sun shield in this direction. One side, the other side, those are all little motors. They will be all started automatically. We have, for all of this, we have redundancy. That means we have, if something isn't working, if something is broken, we have a backup, usually for most of the very important things. And it's part of the plan because we cannot service it. We have those things that jump in and then would help us still to unfold the telescope, even if one thing isn't working. We were really careful to not do single point failures there. Now we have the sun shield separated. Now comes the secondary mirror and the primary mirror. And there we are. We have it unfolded and ready to do science. Okay, I think that's the end
Beautiful.
from my side. I have more slides if people have questions.
That's a wonderful slide set. And Bet just chimed in saying that, for people who aren't scientists and don't know much about this, it's a wonderful way to understand it. So that's really nice.
I thought it was a great idea to show the difference in size between the segmented mirror of the James Webb and the Hubble having the single mirror, and that this thing's massive compared to the compared
Yeah,
to.
I like the tennis court
Huge, no?
analogy. And for those retirees out there, I guess the Hubble would be pickleball size, and the Webb would be tennis court size. That's very nice. I have a question of my own watching this. I see that the mirrors are out there in the vacuum of space, but space also contains micrometeorites. How are the primary mirrors protected from, say, random micrometeorites?
There's no protection for them as of now, but the people have reassessed the risk of micrometeoroids at L2 and came to the conclusion this is some risk you can take because there's just not that many out there in this specific location. So obviously there's always a chance that there's like a really crazy oddball meteorite coming somewhere, but you can never prevent this kind of chance. So people have made the calculations, the risk is low. We can do this on this risk.
Nice. And Andy, you went to Goddard. Did you say you went to Goddard to see it being constructed?
No, I had the opportunity, but I never went. Unfortunately, I didn't.
Oh, I saw it in its initial stages, and that's why your background there reminds me of the clean room, and we got to go into the clean room, and it was very.
Well, this is Jay now. A couple of years ago, I was giving an eclipse lecture, so maybe it was just after, maybe around 2017, before or after it, and somebody came to my lecture at Goddard and said, "I'm working on the James Webb team, and it's in the clean room now, being opened for the last time fully before launch." So after lunch, we went over into through a glass, of course, into this huge room, and there it was standing there with its golden mirrors. So I have my own photo of that I could share with you, and I'm excited to have seen the golden mirrors of James Webb.
I would love to see that photo if you have that. That'd be really nice. We have a
so
question.
The picture that Andy has in his background, by the way, this is at Redondo Beach. That's when it was first then assembled together with the sun shield. I saw it there that was the last time I saw the telescope, was when the sun shield was on, and it was all together. In Goddard, I saw it too, but it was only the mirror. And that picture, that was once it came to California.
Well, a week or two after I saw the Goddard clean room, the American Astronomical Society met in California, and the news people were taken, public relations people were taken to Redondo Beach to see the sun shield. So I've actually seen both halves, but not together.
Beautiful.
I wish you luck with a successful unfolding.
No.
I wanted people to think it was actually in my living room here, but I guess they didn't know that. I just love that picture myself because it's one of the few pictures that it's actually, as we're all talking about, it was done in stages, right? And this is one picture where it's completely opened up and almost as if it was in science mode, Yeah.
You need your clean room uniform on though, Andy. In order
I could have brought one from the hospital if I knew.
We have a question from Dr. Larry Fultz from the Westchester Amateur Astronomers. Larry is a regular attendee to these interviews. He wants to know, will the Webb be able to look at the entire sky, or does its orbit need to be shielded from the sun and eliminate some sectors of the sky? Excellent question.
Very good question. So yes, as we are in one point in space, we will have to have it shielded from the sun. It will not be able to look in the sun direction. But we're going around the sun with Webb, so at the end, it will be able to see the entire sky over a course of a year.
Nice. And just going back to a question about the slideshow before, you talked about going back about 13.5 billion years. That's pretty, because one of the students just wrote in, she said that's going back almost to the beginning of time. Would you say that that's a correct assessment, going back that far in time?
Absolutely. Yes, that student is completely right. So this is showing you basically, this is the history of our universe. This is the Big Bang going and then coming to our time. So it is like very, very close to the beginning of time. You know, when the universe created and expanded, it was very fast at the beginning, and then it took very long later on. So the first like milliseconds, a million things happened, and the first like couple of billion years, a million things happened, and then it got very slow. So we will look like right after like the very beginning, when it just formed with this first light kind of like observations. And this is what we're going to do. You see this Hubble deep field that you probably all have seen before. That's what was Hubble's attempt to look back as far as they could. They looked at an apparent dark patch of the sky for very, very long observation time. And then all those teeny tiny little galaxies appeared that are like billions of years old. And we will do the same with Webb, but we hope we will see even more than that. Further galaxies, further, very smaller galaxies, first galaxies, the first galaxies ever. This is kind of the plan.
Wonderful. I like the dark age. Now, can you explain the dark age segment right there and why it's called that?
The dark age.
Yeah.
Well, there was just no light was formed at this time, and I need to go back to really all my cosmology lectures to remember exactly what kind of processes happened there. But it is before the matter was so dense together and hasn't really separated yet that light couldn't get really through all of the matter and was just scattered all the time. So the universe wasn't very transparent. And we haven't had any matter formed in stars. So we hadn't the stars being collapsed and then starting fusion, because that's what the light is, right? We have a star producing light through fusion, and that hasn't happened yet. So it was also very clumpy and dark and cloudy, but no star has formed during this time.
Andy, could let me ask another question? They're coming in here, an elementary student from New York. I love this. She has a very simple question. Why is the mirror gold?
That's a great question. So the mirror is gold because it best reflects infrared light. So it's specifically made for infrared lights. Gold is perfect for that, and that's why it's gold. It's a very, very thin layer of gold, though, because if you look at this mirror, the amount of gold is about as big as a golf ball that we put on this mirror. So you can imagine how thin that layer of gold is at the end.
Right. That's very nice. I'm just looking at the hexagon shape too. Now, the hexagon is one of those perfect shapes in nature because it looks like a carbon atoms. It looks like a beehive. So, is there any reason why the hexagon shape was chosen out of all the possible shapes of interconnectedness?
No, I don't. I'm not aware of it. I think it's just really the best shape that works. It's the least amount of corners that you would need to get this like intersected like this. Obviously circles wouldn't work, right? Because you would have like space in between. You want something that really fits together.
Yeah.
And that you still want it to become at the final shape something round. So you want to do a combination of both of those things.
Yeah, because it reminds me of a chemical poster with carbon, forming to form diamond in that same kind of.
Yeah,
form.
yeah.
That's very nice. Andy, I know you had a couple other questions too.
Well, question I had, I guess maybe I'm going ahead a little bit, but will the Hubble complement the Webb during any kind of science observations? Would one telescope does one thing and one does the other? Are they going to be used together to do science on a specific project?
Yes, I think so. If Hubble keeps up with its lifetime, we all hope so. It's still growing very strong. It's nothing particularly planned in the first round of observations yet, but I think that was always kind of an idea floating around to do those observations together. Obviously, Webb will look at things that Hubble already looked at in the past, and then we will compare those images and can look at them in the visible and in the infrared.
Well, I have to say that I had not in my wildest dreams that I ever think that the Hubble and James Webb would be doing science at the same time. And I've interviewed several astronauts that have done the Hubble Space Telescope repairs, and it's amazing what they did to the telescope over this period of time. And it's real a shame that we'll not be able to do any more repairs on the Hubble as well. So let's hope that we can get some more great science from both of them now.
Andy, doesn't
Yeah.
the Hubble have a Danbury, Connecticut connection with that? Wasn't the mirror
It has,
manufactured?
yeah. Hughes, Perkin-Elmer ground the mirror. Hughes had a lot of things to do with the science, and I was invited to. It was 25 years of the Hubble. This is from the time the project was started, not 25 years in space. And here at the Norwalk Maritime Center in the IMAX Theater, I get invited to this very special event of an IMAX movie that was made of the Hubble being launched.
saw that.
And
Oh yeah, I remember that.
yeah, and so when I went with the guest, that I think that theater holds maybe 300 people, something like that, or 200. And so they said, anybody who here was involved with anything to do with the Hubble itself, stand up. And 2/3 of the people stood up in the audience. So there were many people in Connecticut and the Long Island, the areas in the tri-state area that had a lot to do with putting the Hubble together and making what it is today.
I wish I could have been a fly on the wall when the first images came back from the Hubble, and they're like, "Oh dear."
Well, I did talk to Story Musgrave about that. He did the eyeglass mission to correct
Right.
the mirror, and they at first they wouldn't even do any. They when they did repairs, they only did them in darkness. They were worried that if they did them in light, there would be too much heat, or so there'd be a problem. So you can imagine, every 45 minutes it's light, and then every 45 minutes it's dark. And they did all their work in the dark at first until they realized that in missions afterwards, they did them in day and night. So it was, very, very cold there. And of course, he said his suit wasn't working, that well every once in a while. So these astronauts really risked their lives for us to
Yeah, they
have.
needed a stronger union or something. I'm telling you, working in the dark and in a cold damn
Oh,
suit.
they didn't care. They didn't
What
care.
amazes me about that, just a little sidetrack here, is that, and I'm not going to jinx anybody or anything, but the fact that we've been able to pull off repair missions under these conditions with constraining suits, with sweat, with 45 on, 45 off, I'm fascinated, and the fact that they could actually go up there and devise a repair for the Hubble so eloquently. I mean,
Yeah.
my uncle would have taken it
Yeah.
and whacked it a few times,
I spoke to.
the fact they were able to do that and have these gorgeous images that I've had posters in my classroom of these the pillars of creation and all those wonderful things. So Nora, what do you expect? I know it hasn't even gone out, it hasn't launched yet, but what are you expecting image wise? Just from the beauty aspect of it, what are you expecting to see?
So image-wise, Webb will do a lot of spectra. That is also very different from Hubble. Hubble did some spectra, but Webb's big capabilities are also going to be spectra. This is always harder to bring to the public because spectra are not that exciting. So I'm personally excited about spectra. But if I would have a guess, what would be the first images we will see? It would be probably the pillars of creation that we all have seen with Hubble, those little fingers where all the stars are born, and they will look different because we will be able to look really into those clouds where the stars are born, and you will see so much more stars and stuff than we would see with Hubble, and then you can combine it even also with the Hubble and make a false color image with it, and it will look pretty amazing.
Is there a way you can sort of equate resolution to this, like comparing it to the resolution of the Hubble? As far as, is there a way you can quantify this?
I don't think I can quantify this. It's more the sensitivity than the resolution that will be better. So it means we can see fainter objects and objects further away with a bigger mirror like that as well.
Interesting. And Larry, again from WAA, show us GN Z11, GN-Z11. And
sorry, what?
Larry, can you come on and explain that for a second to the audience?
Want me to explain it? GN-Z11 was the farthest galaxy that Hubble has in it.
Oh, that's, yes, I'm very,
Okay, sorry.
Yeah,
That's,
that little-
I did not get the context there.
It's the little red blotch, and of course, in
Yes.
Hubble, it's got a few pixels, but it would be very cool to resolve that, which Webb has a much.
That will be definitely on the plan. Yes.
good. We're gonna hold you to that. So what do you, now, what was your team like? Because a student here, I had the same question as a student. The student, and I want to know, what was it like to work with a team on this, and what specifically did your team do, and did you kind of go from one sort of group to another during the whole process?
Yeah, this is a great question. So my team is very international. So I work with the European team, but obviously from very different countries in Europe. So we are Germans, from Spain, from Italy, from France, from England, Scotland, and all, like a lot of different countries. And I particularly work on one of the instruments of the telescope. It's called NIRSpec. It's the Near Infrared Spectrograph. And that is the instrument that was delivered by the Europeans, by ESA to NASA. And one of the deal with this delivery was that they also provide expertise, 15 people around that number to come here and work. So that it was part of the deal between NASA and ESA. And I'm one of those people. I'm here to, we calibrated the instrument and looked at it during those so-called cryo-vacuum tests that we did in Goddard and in Johnson, where we put the whole telescope and the instruments into this big cryo-vacuum chambers, and we simulate space conditions. And there we did that for 3 months, and we again worked in shifts and looked at our instrument and made tests and made sure everything is working. And yeah, so it's been amazing working in my team. My team is actually also very diverse, gender balanced. So we have almost 50% women. And that honestly makes a very big difference. It is a great team. We have a really great team atmosphere. We do a lot of things together. I'm friends with most of those people in my team, just also outside of work. And I've loved every moment I work with those people.
That's great. Now you said the cryo vacuum chambers, so that's basically simulating as close as possible the conditions of outer space. Can you give us a temperature in Kelvin, or what that would be?
Good question. I have no idea. I think I'm really, really bad with numbers. I would have to look this up. Somebody else probably knows this immediately. What are those temperatures? It is very, very cold. Those chambers, especially the one we used in Johnson, were already used for the Apollo mission. So this is one of the biggest chambers in the world, where we put like the entire, also the mirrors in it, the entire upper structure of the telescope, which we call Otis. And then we cooled it down, and that was quite impressive to cool down such a big thing.
You also must have been biting your nails a lot, just making sure, please don't let anything go wrong. And I'm
sure, but I'm also very confident in that people did everything possible to make this go well. You know, we've put so much work into this. The engineers have worked so hard on this, and we all know that this is our only shot. I'm pretty sure we are best prepared that we can be. So I am nervous, but just because that is my nature. But I'm not really worried.
That's great. I like confidence in a scientist.
I got a question.
As a teacher, you know, we usually get things from the lowest bidder. The astronaut's prayer was, as you're sitting on the spacecraft, was, please let this go well, because we know it's been made by the lowest bidder. Does the same thing work with this kind of mission? Do you have the lowest bidder only, or do you get to choose your vendors, things like that?
So I am honestly not 100% sure how it works with NASA. I can tell you how it works from ESA, and I think this is in the same way. I work on different missions as well. You have usually in a competitive phase, you have usually 2 industrial competitors that provide you with a concept, and it's not the lowest bidder. It's the one who basically does it in the best possible way.
Good.
Like also stays in all the requirements for the mass, also in the cost, obviously. But it's not really that they give you like a very different like offer in terms of costs. It's really the whole picture. It's like, did they manage to fulfill all the requirements we gave them?
As we would say in the US, the best bang for the buck, the best value for the money.
Yes,
Sounds-
exactly.
That's great. Andy, got anything for us? Because I got a bunch of questions here from kids, but I want to have you do your thing too.
Oh no, just one quick question because I want the kids to ask more other questions. We talked about keeping the telescope cool and the cryogens. Will the James Webb lose its sensitivity after a period of time? Yes, if it during its age being.
Not much. So the limiting life factor for Webb is actually going to be fuel, because so it will unfortunately not last as long as Hubble, because we are on the semi-stable point, and I always say semi-stable point on purpose because it is not 100% stable. We have to do little course corrections over the time of its lifetime. So once we run out of our fuel, we will not be able to keep this orbit any longer.
So that's the largest factor, not the cryogens.
That's the largest factor. Yes.
Thank you.
What type of a student wants to know what type of booster will be lifting this to L2?
It's an Ariane 5.
Mhm.
I have honestly not the specifics on what kind of boosters they have. It's the standard configuration of Ariane 5. We, as people might know, with the European Space Agency already moved on to Ariane 6. This is our newest rocket, but we kept the Ariane 5 specifically for Webb because this is what it was designed for. Yeah, it was really specifically designed for this rocket. So that's why we will still launch an Ariane 5, which is a super reliable rocket. It launched not millions. It launched a lot of things into space. So that is going to be our launcher.
And like you said before, the beginning of our show, having that extra momentum from launching down by the equator also helps as well.
Exactly. Yes.
Nice. Let me ask one more. I'd like to do like gender equity here too. So let's go back to the boys. The girls have been kind of chiming in here as they do in my classroom too. It used to be the other way around. It used to be the boys would ask all the questions and the girls would be quiet. Now the girls ask all the questions. So let's go to
That's perfect.
one of my friends' classrooms. Michael would like to know how he can. I'm going to paraphrase this. How can he get a job like yours? Basically.
Awesome question. Well, stay in school. Number one, go and study math and physics, or go and do engineering or aerospace engineering. That are all different pathways to working on projects like this. NASA has great programs for young interns and internships to get your feet wet there and look if that's really something you want to work with. So always look out for those kind of programs and apply to them. Even if you think you are not ready yet, just apply. I tell this, especially I tell this to young girls and women all the time, because women and girls tend to be even more hesitant to this and not apply to jobs that they think they're not 100% a fit to. I always say apply. Just get it out there, get yourself out there. You never know what they're looking for. And then just follow your interests on this. It will come very naturally to go if that's what you want to do, to go and work for one of those projects.
And then we have a question. I don't know who this is from. It just says, "Did you see the movie Hidden Figures? And did you?"
Yes,
like
of course, of course, I loved it. Yes.
That was a great movie. That was
yes.
Cool. And I mentioned this at the beginning. I might have been before we went on the air, but a couple of people said they liked your shirt. Can you tell us a little bit about your shirt?
Yeah. So this shirt, I designed that. I do a little bit graphic designing as my side hobby, and I got really lucky to combine this with my science interests too. So, and you can buy it. It's on Cotton Bureau. I can give you the link later.
Yes.
And yeah,
post it. I'll post it to Facebook later also, and pass it around. That's great. So you're a graphic designer also when you're not working on things like this?
It's a hobby. I'm a hobby graphic designer. Yes.
Oh, don't be modest. That's great. What else have you done with your graphic designing?
Just like, it's hard to show those things because many of them were done for conferences. I like to do graphics on so the slides unfortunately are not all my my credit, that was our graphic designer, our really officially graphic designer at ISA, who did this amazing slides. But I always like to do my talks in the most like visual way possible. So that's something where I usually go crazy, is doing talks. Yeah, and sometimes just things for myself.
I know Andy and I are, and a lot of other people are visual learners, so we like to see those kinds of things. A lot of my students are visual learners too. Textbooks are wonderful. It's also nice to have the illustrations.
Yeah, same for me.
Yeah. Jay's textbook, the Cosmos. It's his textbook for Williams College. It's got wonderful graphics. It's one of the nicest textbooks that I've used.
Well, thank you very much. I appreciate that.
You're welcome. You're welcome. You've taken so many of those pictures, Jay, especially the eclipses and the sun and everything. And I had a question about the solar shield before, because I've been following the Parker mission, and my students and I know that the sun shield on the Parker mission is keeping it at a very, very comfortable temperature. What do you know what the temperature would be for the equipment behind the solar shield? What it's keeping the temperature at? And feel free to use Celsius.
Yes. Yeah. I had this in this website over here. 85 degrees Celsius. It's the hot side always. I think it's like 180 Fahrenheit or something.
Yeah, it makes a nice cup of tea.
Yeah, it's pretty hot.
Yeah, but they'll function at that temp. That'll be a constant temperature, I guess, right?
Yeah, the electronics are fine with this. We also have our solar panels on the side. Obviously, they need this. So yeah.
Great, that's great. I know you have to get going because you're a very, very busy scientist these days, especially these days. And we wanted to thank you for coming on. And Andy, anything we haven't covered that I'm trying to think that we haven't covered yet?
Well, I don't think so. I think it's been just a wonderful experience. And Nora, thank you so much for being with us. And these wonderful graphics that, as Charles said, that we're able to look at and, get the full picture in a short period of time. So thanks very much for being with us.
What are we looking at here? I just
I just wanted to show this since we talked about this for a second. That was the sketch on a napkin.
Oh, from 1996?
From earliest time, from 1996, how they envisioned Webb will look like. And if you look at it, it has similarities, right? We see the sun shield, but underneath we see like the mirror. It's kind of folded already. So that's actually then later on, I think that was one of the earliest proposals, how the telescope should look like, came basically from that sketch.
That's right. And I
thought that was a fun thing to show.
Thank you.
I love designs on ideas on napkins. Like, it's funny when
yes, right.
There's this Beatles book I have. It shows them writing their songs on a hotel stationery in Manila. So you never know where good ideas are going to pop up from.
That's very common. It's a very common thing. Yeah. And thanks for sharing that, because I've talked to some people. Their entire careers are involved with the telescope. They've been on this telescope project for their entire career. And I just I wish everybody good luck. Like you said, you're a little nervous, but you're very confident, which is great. And to hear that we have all these redundancies, so that in case something goes wrong, something else will take over. And I just can't wait to see the first images.
Yeah. Now, are you going to be in French Guiana for launch, or are you just going to watch it like the rest of us?
No, I'm going to be here. I'm going to be at the Space Telescope Science Institute watching it. Well, we have the Mission Operations Center is here in Baltimore. So it will be done from here. Once it's launched, we will have contact. And then the people from here will take over. So I'm going to be as close to the control stations as possible.
Okay, I just have a tip for you and your team. Don't clap until it achieves its mission. They drive me crazy. I'm Italian, I'm superstitious, but these people clap for every milestone. No, don't. You're jinxing it.
Well, we have to wait like a month before we can clap, really, right?
Oh, good.
With this mission.
Okay.
6 months for the first imaging, right?
Yeah.
That's great. Well, everybody, we've got a bunch of people saying thank you for coming on. Students, teachers, many I don't even know. And thank you for coming on, Nora. It was a wonderful talk. And hopefully we can maybe get together again when the mission's in full speed and we can tell us what's going on. That would be wonderful.
Yeah. Yeah, it was fun. Thanks for having me.
It was wonderful. Thanks. And thanks, Andy, for being co-host again. It's always fun.
Oh, thanks for the invite. Are you kidding? Love it.
And thanks to our regulars and Larry for
Yeah.
all these good questions and Jay for coming on and love my regulars and thanks to everybody else and have a great weekend. And Andy, I'll catch up with you soon. And Andy, want to plug your next show coming up on Cosmic Perspectives?
Yeah, it's going to, my shows air on, well, I'd say everybody will be using internet. It's wpcan.org, and it's the fourth Saturday of the month. It's 10 a.m. to 11 a.m. Eastern Time, and this month's guest would be Dr. John Mather will be talking about the web with me a little bit, and I'll also have the adventure journalist Jim Clash, who's done all these crazy things, and he's got a ticket on Virgin Galactic, so...
Oh, great. That's really fun. So this will be Thanksgiving weekend, Saturday, correct?
Yes, that's right.
So
Yeah.
when we're all still getting over our tryptophan from the turkey, we'll have a nice show to watch.
Yeah, my show's on Christmas Day this year also. Thank goodness it's recorded.
That's great.
Thanks for asking. And the one thing to say also is that the radio station WPKN is a partner at NASA with the Museum Alliance, and there were only 2 radio stations in the country that were selected. So I'm very proud to say that the radio station is basically all volunteer, and we are also partners with NASA. So.
It's a very famous station. You got a nice write-up in the New Yorker magazine that was really nice, talking about how the diversity behind the station and how it's been a really good voice for people through the years. I was very impressed reading that article. I really didn't know all that.
It was very special, and to have that kind of media attention has been wonderful for the station, because basically we have 2 people that get paid. One is the full-time employee, one's the general manager, and all the rest of us are volunteers. We do our own engineering, most of us, and our own shows and our own editing, and but all that to bring, things like this to the public. So
and most people don't know you have a hamster powering your generator in
and I have a real job. I repair medical equipment on top of that.
Oh, that.
That's not my real. That's what takes up most of my time and of course, my family. So
that's great. Well, it's a pleasure. Thanks everybody for coming on.
I thought that NASA gave you an RPG to power the station.
I wish. It would be nice.
That'd be nice.
Who knows? Someday,
Well, let's do a show again soon, Andy. And
yes, absolutely.
Thanks, everybody.
Thanks for being here, Larry.
Project, and thanks for joining Science at Home interview with me, Charles Folgo, and Andy Poniros, and everybody else. And Nora, thanks again for coming on, Dr. Nora Leutzgendorf, and good luck with everything.
Yeah, good luck.
Thank you.
Yeah, we'll be in touch soon. Thanks, everybody. Have a great weekend.
Yeah.
Take care.
Yeah.
Bye.